long before dark matter became one of the greatest mysteries in modern physics. Astronomers believed they had a relatively good understanding of the universe. By the early 20th century, scientists could calculate the motions of planets, predict eclipses, and explain how gravity governed the movement of celestial bodies. Newton's laws had successfully described the motions of objects for more than 200 years. And many physicists felt that gravity was one of the most well-understood forces in nature. But the universe had a surprise waiting. The first clues emerged not from individual stars, but from gigantic collections of galaxies known as galaxy clusters. These clusters are among the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies spread across millions of light-years. To visualize their scale, imagine replacing every grain of sand on a beach with an entire galaxy containing hundreds of billions of stars. Even then, you would only begin to appreciate the enormous size of these cosmic structures. In the early 1930s, Swiss astronomer Fritz Zwicky turned his attention toward one such structure called the Coma Cluster, located more than 300 million light-years from Earth. The Coma Cluster contains over 1,000 galaxies packed together by gravity. Zwicky wanted to understand how these galaxies moved within the cluster, and whether their motions matched the predictions of known physics. To do this, he measured the velocities of individual galaxies as they orbited within the cluster. What he found was astonishing. The galaxies were moving extraordinarily fast, far faster than they should have been according to Newtonian gravity. The amount of visible matter in the cluster should determine how strongly gravity holds everything together. If astronomers could estimate the total mass of all the visible stars and galaxies, they could calculate how fast those galaxies should move. But the numbers didn't match. Not even close. The galaxies were moving so rapidly that, according to the visible matter alone, the entire cluster should have flown apart billions of years ago. Imagine watching a carousel spin faster and faster. Eventually, the horses would be thrown outward because the structure could no longer hold together. That was essentially what Zwicky observed. The galaxies appeared to possess far too much kinetic energy for the amount of gravity that visible matter could provide. Yet, the cluster remained intact. Something unseen had to be holding it together. Zwicky concluded that there must be a vast amount of invisible mass hidden throughout the cluster. He called this mysterious substance Dunkle Materie, German for dark matter. At the time, his conclusion was largely ignored, partly because his measurements were difficult to verify, partly because the idea seemed extraordinary, and partly because Zwicky himself was known for being outspoken and controversial. Many astronomers assumed there must be an error somewhere in the calculations. After all, proposing that most of the universe consisted of invisible matter sounded almost absurd. For decades, the mystery remained unresolved. Then, in the 1970s, a second discovery changed everything. This time, the evidence came not from galaxy clusters, but from individual galaxies themselves. At the center of this breakthrough was American astronomer Vera Rubin. Rubin spent years studying the rotation of spiral galaxies. These magnificent cosmic structures contain hundreds of billions of stars orbiting around a central region. Our own Milky Way is one such galaxy. The expectation seems straightforward. Just as planets farther from the Sun move more slowly, stars farther from a galaxy center should also orbit more slowly. The reason comes directly from gravity in our solar system. Earth travels around the Sun at about 30 kilometers per second. Neptune, much farther away, moves at only about 5 kilometers per second. The farther you get from the dominant source of gravity, the weaker the gravitational pull becomes. Galaxies should behave the same way at least. That's what the equations predicted. But when Rubin carefully measured the orbital speeds of stars at different distances from galactic centers, she discovered something profoundly strange. The stars refused to slow down, instead of declining with distance. The rotation curves remained nearly flat dot stars. At the outer edges of galaxies moved, almost as quickly as stars much closer to the center. This shouldn't have been possible, according to everything astronomers knew at the time. Those outer stars should have been moving too fast to remain gravitationally bound to their galaxies. They should have escaped into intergalactic space long ago, yet they didn't. Something was providing additional gravity, something invisible. Rubin's observations were so consistent across different galaxies that it became increasingly difficult to dismiss them as measurement errors. Again and again, astronomers observed the same pattern. Everywhere they looked, galaxies appeared to contain far more mass than their visible stars, gas, and dust could account for. The simplest explanation was that galaxies were embedded inside enormous halos of unseen matter. These dark matter halos extended far beyond the visible edges of galaxies, creating the extra gravitational pull needed to keep rapidly orbiting stars from escaping suddenly. Fritz Zwicky's forgotten idea no longer seemed so strange. It began to look unavoidable. Over the following decades, additional evidence accumulated from multiple directions. Astronomers studying gravitational lensing found that light from distant galaxies was being bent by invisible concentrations of mass. Cosmologists examining the large-scale structure of the universe discovered that galaxies appeared to form along vast cosmic filaments that required dark matter to explain their growth. Even observations of the early universe suggested that ordinary matter alone could not produce the structures we see today. The case for dark matter became increasingly compelling, and yet there was a problem. All of this evidence was indirect. Scientists could see the effects of dark matter. They could measure its gravitational influence. They could map its apparent distribution across billions of light years. But they still couldn't see the dark matter itself. Imagine standing in a forest. After a snowfall, you notice enormous footprints crossing the landscape. Branches are bent. Snow is disturbed. The evidence clearly suggests that something massive passed through. But despite following the trail for miles, you never actually see the creature responsible. That is the situation physicists find themselves in today. Dark matter leaves footprints everywhere, in galaxies, in galaxy clusters, in gravitational lensing maps, in the cosmic web stretching across the universe. Its influence appears undeniable, and yet the thing itself remains invisible, which raises a fascinating possibility. What if dark matter truly exists, but is unlike anything we've ever encountered? Or perhaps even more dramatically, what if these footprints belong to something entirely different from what we currently imagine? Because, as we'll discover next, the deeper scientists search for dark matter, the stranger the mystery becomes.
If dark matter cannot be seen, touched, photographed, or directly detected, then how can scientists be so confident that it exists? It's a fair question. In science, extraordinary claims require extraordinary evidence, and the idea that most of the matter in the universe is invisible certainly qualifies as an extraordinary claim. The answer begins with one of the most important lessons in physics. You don't always have to see something to know it's there. In fact, some of the most significant discoveries in science were made long before the objects themselves were directly observed. Nobody has ever seen gravity itself. Nobody has ever photographed a magnetic field. Even black holes remained invisible for decades before humanity finally captured an image of one in 2019. Scientists often discover hidden things by observing their effects on the world around them. And dark matter may be the greatest example of this principle ever encountered. Its fingerprints appear everywhere, from individual galaxies to the largest structures in the observable universe. There are signs that something unseen is exerting gravitational influence on a cosmic scale. The first clue comes from a phenomenon predicted over a century ago by Albert Einstein. According to Einstein's theory of general relativity, gravity is not simply a force pulling objects together. Instead, massive objects distort the very fabric of space-time itself. Imagine placing a heavy bowling ball onto a stretched rubber sheet. The sheet bends beneath the weight. Now place a smaller ball nearby. It rolls toward the larger object, not because an invisible force is pulling it, but because the surface itself has been curved. This analogy isn't perfect, but it captures the essence of Einstein's revolutionary idea. Mass tells space-time how to curve. Space-time tells matter how to move. One consequence of this is remarkable. Even light must follow the curvature of space-time. Although light has no mass, it still travels along the warped geometry created by massive objects. As a result, light passing near a galaxy or galaxy cluster can bend as it travels through space. This effect is known as gravitational lensing. Einstein predicted it in 1915. Today, it has become one of the most powerful tools in modern astronomy. Imagine looking at a distant galaxy, billions of light years away. Between that galaxy and Earth sits another massive galaxy cluster. As the distant light travels toward us, the gravity of the intervening cluster bends and distorts the light. The result can be extraordinary. Sometimes the distant galaxy appears, stretched into giant arcs. Sometimes multiple images of the same galaxy appear in different positions. In extreme cases, the galaxy forms a nearly complete ring of light around the foreground object. These structures are known as Einstein rings. They are among the most beautiful and powerful confirmations of general relativity ever observed. But for dark matter researchers, they reveal something even more important. They reveal mass, a lot of it. By measuring exactly how much light bends, astronomers can calculate how much mass must exist in the foreground. This process works whether the mass is visible or invisible. Gravity doesn't care. It bends light, regardless. And when scientists perform these calculations, they repeatedly encounter the same mystery. The visible matter isn't enough, not even close. In many galaxy clusters, the amount of mass required to produce the observed lensing effects is 5, 6, or even 10 times greater than the amount of matter. We can actually see dot. It's as if an invisible skeleton is hiding beneath the visible universe. One of the most famous examples is the Bullet cluster. This object has become one of the strongest pieces of evidence for dark matter ever discovered. The Bullet cluster is actually two galaxy clusters that collided hundreds of millions of years ago. When the collision occurred, something fascinating happened. Most of the visible matter in the clusters exists as superheated gas. This gas interacted violently during the collision. It slowed down, it compressed, it oppressed, it produced enormous amounts of X-ray radiation that astronomers can observe. But when scientists mapped the gravitational mass using lensing techniques, they found something astonishing. The majority of the mass was no longer located where the gas was. Instead, it had passed straight through the collision, almost unaffected. The visible matter and the gravitational mass had become separated. In other words, most of the gravity appeared to come from something invisible, something that barely interacted with ordinary matter at all. For many physicists, the Bullet cluster represents a cosmic crime scene, and dark matter is the primary suspect, but gravitational lensing is only one piece of the puzzle. The next clue comes from the largest structures in existence, the cosmic web. When astronomers mapped the distribution of galaxies across billions of light years, they discovered that galaxies are not randomly scattered throughout the universe. Instead, they form a gigantic interconnected network. Immense filaments stretch across the cosmos. These filaments connect galaxy clusters, like highways connecting cities. Between them lie enormous voids, where very few galaxies exist. The scale is almost impossible to comprehend. Some filaments span hundreds of millions of light years. Together, they form what scientists call the cosmic web. The question is, how did this structure form? To answer that, cosmologists run enormous computer simulations. These simulations begin shortly after the Big Bang. They include known laws of physics and allow virtual universes to evolve over billions of years. When scientists include dark matter, something remarkable happens. The simulations produce structures that closely resemble the real universe. Galaxies form, clusters emerge, the cosmic web appears. The virtual universe looks strikingly similar to what telescopes actually observe. But when dark matter is removed from the equations, everything changes. The simulations fail, galaxies struggle to form. Large-scale structures never develop properly. The universe that emerges looks nothing like reality. This is one of the strongest arguments in favor of dark matter. It doesn't just explain one observation, it explains many observations. Simultaneously, galaxy rotation curves, galaxy clusters, gravitational lensing, cosmic structure formation, the cosmic microwave, background. Each line of evidence points toward the same conclusion. There appears to be far more mass in the universe than visible matter can account for. And yet, despite all this evidence, an uncomfortable fact remains. We still haven't directly detected dark matter, not once, no. Telescope has photographed a dark matter particle, no. Laboratory has captured one definitively, no. Experiment has yet provided the smoking gun. Everything we know comes from its effects, its gravitational fingerprints, its footprints in the cosmic snow. Imagine arriving at a beach after sunrise. You see footprints stretching across the sand. You can estimate the size of the creature, its speed, its direction, its weight. You know something passed through. The evidence is undeniable. But until you actually see the creature itself, some uncertainty remains. That is precisely where science stands today. Dark matter leaves, footprints everywhere. It shapes galaxies, it bends light, it influences the evolution of the universe. It appears woven into the very structure of the cosmos, and yet the thing creating those effects remains hidden, invisible, silent, unknown. Unknown, which is why dark matter remains one of the most fascinating mysteries in modern science, because the evidence for its existence is overwhelming. Yet the true nature of what it actually is remains completely unresolved. And, as we'll see in the next chapter, the deeper scientists search for dark matter itself, the more puzzling the mystery becomes. If dark matter truly makes up roughly 85% of all matter in the universe, then a simple question naturally follows. Where is it? For nearly a century, astronomers have watched its gravitational influence shape galaxies, bend light, and sculpt the large-scale structure of the cosmos. The evidence appears everywhere. Yet, despite decades of searching, nobody has ever captured a dark matter particle in a laboratory. And that is where the story becomes truly fascinating, because modern physics is built upon a remarkable track record of predicting invisible things before discovering them. The planet Neptune was discovered because astronomers noticed irregularities in the orbit of Uranus. The particle known as the positron was predicted mathematically before it was ever observed. Even the famous Higgs boson existed on paper for nearly 50 years before physicists finally detected it at CERN. Dark matter seemed destined to follow the same path. Scientists believed they knew what they were looking for, or at least they thought they did. By the 1980s and 1990s, one candidate had emerged as the overwhelming favorite: the WIMP weakly interacting massive particle. The name may sound technical, but the idea was elegant. A WIMP would possess mass, allowing it to exert gravity. However, unlike ordinary matter, it would rarely interact with light or atoms. That would explain why dark matter is invisible. Trillions of these particles could be passing through your body right now, every second, without leaving a trace. In fact, if WIMPs exist, a vast halo of them is flowing through our galaxy at this very moment. The Earth, the Moon, every person alive, every building, every ocean and mountain is moving through what could be an enormous invisible sea of dark matter. And because WIMPs interact so weakly, detecting them would be extraordinarily difficult, but not impossible. At least, that was the hope, building the most sensitive experiments ever created to detect dark matter. Physicists needed to eliminate every possible source of interference. The challenge is almost unimaginable. Imagine trying to hear a single falling snowflake during a hurricane. That is roughly analogous to searching for dark matter. The universe is full of background noise. Cosmic rays constantly bombard Earth. Natural radioactivity exists in rocks, soil, and even the human body. Tiny particles from the sun stream through our planet every second. All of these signals can mimic the effects researchers hope to observe, so scientists went underground. Very far. Underground, some experiments were built beneath mountains. Others were installed deep inside former gold mines. Some sit more than a mile beneath Earth's surface. The rock above acts like a giant shield, blocking most cosmic radiation. The goal is simple: create the quietest environment possible, the place where even the faintest whisper from dark matter might finally be heard. The liquid xenon, giants among the most ambitious dark matter experiments ever built, are Lux-Zeppelin. These facilities look less like astronomy experiments and more like something from science fiction. At their hearts sit enormous tanks containing tons of liquid xenon. Why xenon? Because xenon atoms are extremely sensitive targets. If a dark matter particle collides with one of their nuclei, it should create a tiny flash of light and release a small amount of energy. Sensitive detectors surrounding the tank can measure these signals. The flashes are incredibly faint. Some involve only a handful of photons, yet modern technology is capable of detecting them in principle. A single dark matter particle striking a xenon atom could announce its existence. Researchers expected that if WIMPs existed within the predicted mass range, these detectors would eventually find them. The logic seemed sound. The calculations were convincing. The detectors were. Extraordinary success appeared inevitable. Past then, something unexpected happened. Nothing. Year after year, the detectors continued operating. More data arrived, more events were analyzed, more false alarms were investigated. Yet, no unmistakable dark matter signal emerged. Scientists improved the detectors. Still nothing. They increased sensitivity. Still nothing. They expanded observation times. Still nothing. Each new generation of experiments became dramatically more powerful than the last. And yet the darkness remained silent. This wasn't merely disappointing, it was surprising. Many physicists genuinely expected a discovery by now. Theoretical models suggested that dark matter should reveal itself. Within these experimental ranges, the predicted particles seemed absent. Or perhaps they had never existed in the form researchers imagined. The shrinking WIMP paradox in science: failing to find something is often just as important as finding it. Every null result eliminates possibilities. Searching for a missing person in a city. Each neighborhood you search narrows the possibilities. The search becomes more constrained. The same principle applies to dark matter. Every experiment that fails to detect WIMPs rules out part of the parameter space where those particles could exist. Over time, that space has become dramatically smaller. The region once known as the WIMP miracle, a range of particle masses and interaction strengths that seemed naturally compatible with both cosmology and particle physics, has steadily shrunk. Many models that dominated theoretical research for decades have now been severely constrained. Some have effectively been ruled out. Others survive only in narrow corners of possibility. The once landscape has become increasingly barren. Looking for the wrong particles, confidence in traditional WIMP models declined. Scientists began exploring alternatives. One possibility is that dark matter particles are much lighter than expected. Another is that they interact even more weakly than WIMPs. Some researchers turned their attention toward hypothetical particles known as ixions. Others proposed sterile neutrinos. Still others imagined entire hidden sectors of physics operating beyond the standard model. The range of possibilities exploded. Dark matter transformed from a relatively focused search into a vast scientific frontier. Every year brings new ideas, new experiments, new theories, and new uncertainty. Ironically, the more scientists learn about dark matter, the less certain they become about what it actually is: a crisis or an opportunity. To the public, decades of failed detections might sound like bad news. To scientists, however, it is something else entirely. It is an opportunity. History shows that major breakthroughs often emerge when nature refuses to cooperate with expectations. At the end of the 19th century, physicists believed they understood nearly everything about the universe. Then experiments revealed anomalies. Those anomalies eventually led to relativity and quantum mechanics. The failure to detect dark matter may be a similar moment. Perhaps the solution is waiting just beyond our current understanding. Entirely new physics lies ahead. Or perhaps we have misunderstood the problem from the beginning. The growing tension today, astronomy and particle physics find themselves in a fascinating position. On one side, the astronomical evidence for dark matter remains incredibly strong. Galaxies rotate too quickly. Galaxy clusters contain too much gravity. Gravitational lensing reveals invisible mass. The cosmic web appears to require dark matter to form. These observations are real. They demand explanation. On the other side, particle detectors remain stubbornly silent. The expected particles have not appeared. The universe seems to be telling us two different stories simultaneously. One says something invisible is out there. The other says, whatever it isn't what you expected. And that tension is precisely why dark matter remains one of the greatest mysteries in modern science. Because after billions of dollars, decades of research, and some of the most sophisticated instruments humanity has ever built, we are left with an astonishing conclusion. We can see dark matter's fingerprints across the cosmos, but we still have absolutely no idea whose fingerprints they are. And perhaps the most unsettling possibility of all is that the answer, when it finally arrives, may look nothing like what we've been searching for. When observations don't fit theory, scientists face two possibilities. Either something unseen exists, or the theory itself is incomplete. This second possibility has inspired alternative explanations that challenge one of the most fundamental forces in nature. One of the most famous alternatives is modified Newtonian dynamics, commonly known as MOND. Instead of adding invisible matter to explain galactic motion, MOND proposes that gravity behaves differently under extremely weak. Surprisingly, this approach successfully predicts many galaxy rotation curves without requiring dark matter at all. To some researchers, this success suggests that our understanding of gravity may be incomplete. However, MOND faces serious challenges when applied to galaxy clusters, gravitational lensing observations, and the cosmic microwave background. In many cases, dark matter still provides a better overall explanation. Yet, the existence of these alternative theories highlights something important about science. No idea, no matter how popular, is immune to scrutiny. The universe is not obligated to conform to human expectations. If observations eventually reveal flaws in our current models, scientists must adapt. Some researchers believe the ultimate solution may combine elements of both approaches. Others suspect that a deeper theory, perhaps involving entirely new physics, will emerge. Just as Einstein expanded Newton's understanding of gravity rather than completely replacing it, the future may bring a more comprehensive framework that makes today's debate seem incomplete. Whatever the outcome, questioning established assumptions remains one of science's greatest strengths. Today, the hunt for dark matter continues on multiple fronts. Particle physicists search for new particles using powerful accelerators such as CERN. Astronomers use advanced telescopes to map dark matter distributions throughout the universe. Space observatories study the earliest galaxies in search of clues about cosmic structure formation. Meanwhile, theoretical physicists explore increasingly bold possibilities. Some propose entirely new classes of particles, including ixions and sterile neutrinos. Others investigate hidden sectors of reality that may interact with ordinary matter only through gravity. There are even proposals suggesting that dark matter may arise from emergent phenomena we do not yet understand. What makes this mystery particularly exciting is that every outcome would be revolutionary. If dark matter particles are discovered, it would represent one of the greatest breakthroughs in modern physics. If gravity requires modification, it could trigger a scientific transformation comparable to Einstein's theory of relativity. And if the solution turns out to be something completely unexpected, it may reveal layers of reality humanity has never imagined. We are living through a remarkable period in scientific history. For the first time, technology allows us to investigate these questions directly. The answer may arrive tomorrow, or it may take decades. But one thing is certain: whatever dark matter turns out to be. Solving this mystery will fundamentally change our understanding of the universe. Perhaps the most profound lesson of the dark matter mystery is not what it tells us about the universe, but what it tells us about ourselves. Humanity has spent thousands of years trying to understand the cosmos. We've mapped the motions of planets, discovered galaxies beyond our own, photographed black holes, and measured the age of the universe with astonishing precision. Yet despite these achievements, we may still be fundamentally ignorant about most of reality. Think about that. Everything you've ever touched, seen, heard, or experienced represents only a small fraction of what exists. The vast majority of the cosmos remains hidden in darkness. Whether dark matter proves to be an undiscovered particle, a modification of gravity, or something entirely unexpected. The journey toward understanding it is one of the greatest adventures in science. It reminds us that the universe is still filled with mysteries waiting to be explored. And perhaps that's what makes astronomy so inspiring. Every answer reveals deeper questions. Every discovery opens new frontiers. If you enjoyed this exploration into one of the biggest mysteries in modern physics, subscribe and join us for more journeys into black holes, dark energy, exoplanets, the Big Bang, and the hidden architecture of reality. Because the deeper we look into the universe, the more we realize how much remains unknown.